right, ready to go. Circuits questions. In order to form an electric circuit, you have to have yeah, all the above. All right, complete path for the circuit. Be called a closed circuit. It's called right? Power source, like a voltage source. Right? Some kind of resistor. Otherwise, you have a short circuit. Right? That's why you do resistor. All right, all the above. Yeah. All right, points on the board. In order for current to flow in a circuit, yeah, you have to have a complete path for the circuit, which is also called a closed switch, closed circuit. Okay. Please flip over to my reference posters. Whoops, wrong button. This one right here. Here we go. Okay. So here's a circuit with a bunch of stuff on it. Some of the things you guys know. Right. Battery source, voltage source. Right. You guys know that one. You guys know resistor. Tomorrow, I want to give you guys a lecture on inductors and capacitors, which is also going to lead to electromagnetic conduction. So it's next couple days, right? And then what about these guys up here? Oh, look, switch, right? So you guys see how that switch is open? That's like if the lights are off, right? That's an open switch where the current cannot flow in the wire. If I turn the light on, bam, that's like closing the switch, right? That's like closing the switch. Right now, there's a path for the current flow. You guys are going to get at least a couple of questions on this fuse. A fuse is like if there's too much current surging through, it's like, well, maybe like here, if you were to go like jamming paper clips in these outlets and these walls, don't do that. There's 120 volts, right? It could shock you, it could seriously hurt you, right? That current would want to go through you and into the ground where the current's trying to go. Now, if there's too much current flooding all at once, then it might burn the fuse out, which could open the circuit, and then the current would be no longer flowing. Okay, so there's a couple of those questions coming up too. All right, let's go back over here. How are we doing on points? I got Candace, Tucker, Sophia, Blake, Chloe. Electrical resistance is measured in yeah, ohms. Right, guys, what does joules measure? Energy, volts. That'd be a voltage or potential difference, right? Amperes is current, and ohms is electrical resistance. All right, Blake in the top five, Chloe in the lead. A closed circuit is one which charge. Yeah, can flow, right? If it's an open circuit, the current cannot flow. If it's a closed circuit, the current can flow, right? It's like your off-on switch, right? If you turn something on, that's closing the circuit. Therefore, the current can flow and all the bulbs turn on, right? Afe, Tucker, Sophia, Chloe, and Blake on fire. When two light bulbs are connected in series, is it the same current always flows through each bulb, or the current is proportional to the resistance? Which one is it? In series. It's one the same current flows through each bulb, regardless of the resistances of the bulbs. Right, so let me bring this over here. Okay. So quite a few questions on this Kahoot, including this question from straight off this poster, which is hanging over my lab closet door, or maybe you guys have your thumbnail notes out. I checked out too. Right. So they said in series, what's the deal with current? And it's that row right there. It's that one right there. That's the question that was just asked. The current is the same everywhere in series. Even if resistor A is 1 ohm and resistor B is like 9 ohms, doesn't matter. It's the same current everywhere. Right. For current, I was using a traffic analogy. Here's a parking garage, and the cars are like driving around town, around these roads. Right. If that's like one stoplight and that's like 9 stoplights, right? All the cars, if there's like a line of 100 cars, they still have to go through all of them, right? It's the same 100 cars everywhere. Okay, you got that? Okay. Tell you what, while I got this page out, let's look at this because there's a few questions coming about uh, other parts of this page. Okay, so for series, the guys, look up here. The voltage drop across each one of these is proportional to the resistance. So again, if it was like 1 ohm and 9 ohms, actually there would be more voltage drop over the 9 ohms than the 1 ohm. Right, it'd be just proportional. Right, so that's for series. Okay. Now, if you switch over to parallel, then the roles all kind of reverse. Right now, the voltage drop is the same across both resistors, even if they're different resistances. So if you have like 1 ohm versus 9 ohms, it's the same voltage drop, right? But the current splits, and how much current goes each way is actually proportional to the other resistor. So, guys, everybody look up here. Let's do some numerical example. Suppose there's 100 amps. You guys got that? 100 amps, make believe. What if I have 1 ohm here and 9 ohms here? You guys got that? Right, 1 ohm versus 9 ohms. Okay, that 100 amps of current is going to split. How much current goes through 1 ohm? I bet 90 amps goes through 1 ohm. I bet the other 10 amps only goes through the through the 9 ohms, right? Because the more current goes through the less resistance, right? So see how the current is directly proportional to the other resistor. Okay. All right, so back to Kahoot. You guys gonna see all those questions come up. Right, we did a little bit of review right there. That'll get you guys caught up here. Party on points. We got Afe, Tucker, Sophia, Chloe, and Blake still on fire. The symbol used to represent resistance in a schematic diagram is. Yep, that's your zigzag. Zigzag line is a resistor. There you go, zigzag. Blake in the top 5. Close. When resistors are put in series next to each other, the overall resistance is greater, right? Larger, right? Here, let's do a poster recap here. Guys, remember resistors in series? You just very simply add the resistors. So if it's like 1 ohm, 2 ohms, and 3 ohms, you say, well, 1 plus 2 plus 3 is 6. Boom. Right. So the more the resistors in series, the more total resistance. You guys have any questions on that one or any of these? If you have any questions, let me know. All right, Adam, top 5. Tucker, Sophia, Chloe on fire. Blake still in the lead. When resistors are put in parallel, the overall resistance is what? Yeah, smaller. Right. Here, since I'm doing a video, in case anybody's watching this video at home, say, wait, why is that the case? Let's do a quick recap here too. Right. Here's resistors in parallel. Here's the math for figuring out total resistance. Right. And or so a few ways to think about this. Like if it was like, suppose it's 9 ohms, 9 ohms, 9 ohms. What's the overall resistance? Well, 1 over 9 plus 1 over 9 plus 1 over 9, reciprocal, boom, we got the answer that way, right? Or the very first question I asked you when we started this electricity section was like guys painting a fence. Like if there's a team of people working on a project collectively and they're working in parallel with each other, and it's the same math for how much time it takes. So if it took 9 hours for this guy to paint a fence, and then same for this guy 9 hours, same thing for this guy 9 hours, but they make a 3-man team, guys, how long does that job take? Only 3 hours, right? It'd be a third of the time in that case, right? So you get kind of simple numbers, right? And if you replace hours with ohms, 9 ohms, 9 ohms, 9 ohms, this is collectively only 3 ohms, right? Because once you run all this math, or if you do 2 at a time, you can do product over sum, right? But that will always show a decreased resistance. Okay? Another way to think of it, how about traffic analogy? Like if I'm going back. Let me go back over here. Right, back over here. Let's switch back over. Yeah, guys, traffic analogy. What if you're driving around town? Now, back in the series days, guys, everybody look up here? Everybody think about this? Everybody look up here, think about this? Okay, right. Okay. Back in series days, every time you add on a resistor, well, it's like adding new stoplights. That makes it harder to drive around. So that's even more resistance as you drive around. But if you're talking about parallel, like rungs of a ladder, every time you open up a new street and put a stoplight on it, then it actually makes it easier to drive around town because now you got more options about how to drive. So that's maybe another perspective of why the overall resistance actually decreases when you put resistors in parallel. All right. So you guys all got that. That is awesome. More points. Next question. As more lamps are put into a series circuit, the overall current does what? It decreases. Right now, this is a two-step problem. Right. The middle step that they didn't quite ask is what guys, what happens to the overall resistance? As you put more and more lamps in series, the overall resistance does what? Goes up. Right. Then switch over to Ohm's law. You guys remember Ohm's law? I equals V over R. Right. So current that flows, okay, so the voltage is the same, whatever, divided by more resistance is less overall current. Right? Right. You guys remember Ohm's law? I equals V over R. Right. That's the missing middle step there. All right, you guys good with that? All right. Ooh, big leader switch. We got Adam, Blake, Sophia, Blake, and Chloe back on fire. As more lamps are put into a parallel circuit, the overall current yeah, there you go. All right, so increases because it'd be the exact opposite of the previous question. Here, let me switch over. Remind you guys what that's working. All right, so again, a two-parter, just like last question. As you put more and more lamps in parallel, the overall resistance decreases. Right? And then switch over to Ohm's law. Say, okay, well, we got the same battery, whatever, right? If you have a decreasing resistance, that is going to correspond to an increasing current. Ah, Ohm's law. And points. Compared to the resistance of two resistors in series, the same two resistors in parallel is? Yeah, less resistance. All right, let's do a numerical example. Suppose you have 10 ohms and 10 ohms. Guys, what is 10 and 10 in series? 20. What is 10 and 10 in parallel? 5. Right? 10 hours of painting fence, 10 hours of painting fence, two-man team. It's 5-hour job now, right? Or how about product over sum? Guys, what's 10 times 10 divided by 10 plus 10? Is that 100 divided by 20? That's also 5. Okay, so 5 ohms in that case. All right. Blake moving up just behind Blake, and Chloe still in the lead. When one bulb in a series circuit containing several bulbs burns out, hint, that opens the circuit. Yeah, none of the other bulbs will light up. Let's look at a schematic diagram because the answer just pops out of this page right here. Right. So here's my voltage source. Here's maybe like 3 light bulbs. Right. Current goes around, and then what if this resistor C, this bulb just like burns out? Doesn't that open the circuit and then no current flows at all? Right. Right. You guys said right. First, you know what? I think the next question might be what happens in parallel. Right. So let's look at that just in case. Right. Guys, what if this bulb burns out in parallel? Do the other bulbs still light up? Yes, they do in parallel because the current can still flow around in parallel. Right? You guys probably string up Christmas lights sometime, right? Christmas lights, and different Christmas lights are manufactured differently. If it's a series setup and one bulb burns out, the entire string of lights goes out. You have to replace the one bulb to get any of those to work. But if they're wired in parallel, and some of them were manufactured this way, if one bulb burns out, the rest of them still light with the exact same brightness as before. You got the same voltage over them, same resistance. So back to Kahoot. Who got that? 3 winners. Who's getting points? We got Adam, Sophia, Blake moved up over Blake, and Chloe still in the lead. When one light bulb in a parallel circuit containing several bulbs burns out, what do the other bulbs do? Some bulbs. Yeah, they'll burn the same as before. Same as before. Let's look at the schematic diagram. Right, so sorry. Right. So this is what I was just showing you, right? So if it's a parallel setup like this, right, and one volt burns out, isn't the exact same voltage drop across these other resistors, and therefore the same current through those resistors, right? Or how about this? What if we did this whole thing backwards? What if you start with just one bulb lit up like this? Right, so you got one, and you attach the second one in parallel. Well, now that one burns bright, right? But the first one is burning just as bright as before. And if you put it on a third one, right now all three are shining really bright. And if you take one off or it burns out, then the other two are still shining. Okay. Just like when I gave you guys some Christmas lights and the cell phone chargers, you guys did that too. And that? Right. You guys good with lights, the gold answer? Right. How are you doing on points? Tucker on fire and in the top 5. Sophia, Blake, Chloe. In a simple parallel circuit, is it current through each branch is always the same, or voltage drop across each branch is always the same? Which one is it parallel? Yeah, it's voltage drop is the same, right? Even if the resistors are different. Let's go back to this one right here. Guys, remember this poster? It's hanging above my lab closet door. It's this rule right here. And so parallel setup, right? Now the current splits, right? Now if these resistors are the same resistance, the same number of ohms, then the current will split exactly half and half, right? But if they're different than each other, then more current follows the path of least resistance, right? And then less current goes to greater resistance, right? But the voltage drop is the same regardless. If this is like a 9-volt battery, it's 9 volts over that guy. It's also 9 volts over that guy. Okay. Or voltage is kind of like pressure. Right? So they got the same voltage drop in parallel. Even if they're different resistances and ohms. All right, you guys get there? So Kirchhoff and friends. Sophia moving up. Blake, Chloe still in the lead. And the simple parallel circuit, so we're sticking to parallel, is it current through each resistor is inversely proportional to the resistance. Current is divided in each branch. Voltage across each branch is the same, or all of the above. Yeah, there you go. All of the above. Those are all true. All true. Right. Right. So yeah, voltage is the same across each one. That was the previous question. So we just did the come on. We just did that one. Yeah, the current divides. And now the red one, I want to point this one out on the poster. Right. Why is it the current flows is inversely proportional to the resistance for parallel? Right. Switch over here. Right. That is this row right here. That's the very last row on this page, this poster. Right. So here, you guys ready for a numerical example? You guys ready? Ready? Okay. What if I have 100 amps? You guys see 100 amps? And resistor A is like 1 ohm. Resistor B is 9 ohms. You guys got that? 1 ohm versus 9 ohms? Right. You think the current's going to split like 90% goes one way and 10% goes the other way? Right. But where does more current go? Across 1 ohm or across 9 ohms? Probably across 1 ohm, right? I bet 90% of the current, like 90 amps, is going to go across 1 ohm. And the other 10%, like the other 10 amps, is going to go through the 9 ohms. That's exactly what this expression says right here. Right? The current through branch A is proportional to resistor B. Ooh, okay. That simple parallel setup. Right, guys good? Right. Kind of like if you're driving around town, you see the road split at a fork. Say, okay, there's one stoplight down that road. There's 9 stoplights down that road. I bet most of the traffic's gonna go through one stoplight. That makes sense, right? All right, Blake, Tucker, Sophia, Blake, flow away. Fuses and circuit breakers are used to prevent overloading, break the circuit when too much current is being used, protect us, all of the above. Yeah, all the above. There you go. All right. Adam, Tucker, Sophia, Blake, flow away. A short circuit occurs when the very short wires are used in the circuit. The circuit lasts for only a short time. The positive is connected directly to the negative. It's one of those three. Yeah. All right. All right. That's what I'm for. Positive directly connected to the negative, right? Or if you have like negligible resistance. All right. Right. You guys know that? Oh, Tucker, you said what something on fire, right? It was a what do you call it thing you wrap the gun in? Yeah, right. Because you created one of those, a short circuit, right? Yeah. Yeah. How you do it? Two lamps got thick filament, thin filament. So think low resistance and high resistance. Connected in series, the current is greater in the lamp with ooh, one winner. One winner. All right. All right. Casey for the win. All right, so that is this row right here. It's this row. This row. Right. The current's always the same in series, even if they're different resistances. Right. Guys, this is the first of a set of questions. There's going to be a few questions about thick filament, thin filament. Now, you guys remember yesterday, the lab you did. Here, let me see if I can dig up the poster for yesterday's lab. I got it right here. Got it right here. Okay. You guys remember yesterday was this lab? Right. I have this labeled wire, but it could be Go cylinder. It's the same idea. Is that if it's thick, that's a large cross-sectional area, which is low resistance. If it's thin, then the opposite, that's a high resistance. Okay, so we got that. So that aside, okay. Now this particular question, suppose you got two different resistors, they still have the same current as long as it's in series, right? Like if it's one stoplight here and 9 stoplights here, and you have like a stream of 100 cars, all 100 cars have to go through all the stoplights, right? Right. Guys, are you ready for the next question? The next question is going to be basically these rules here. You guys ready to navigate these rules right here? You guys see this poster hanging above my lab closet door? Right. They're kind of in jumbled order, but the next few questions are all coming straight off that page. All right. Oh, yeah, case of points. Two lamps, thick filament, thin filament, so low resistance and high resistance, connected in parallel. The voltage is greater across the lamp with a voltage drop. Right. Ooh, two winners. Two winners. It's the same voltage drop. Let's see, where's that on this page? Is that should be here too? Yeah, that's this row right here. Look, two resistors in parallel, always the same voltage drop, even if they're different resistances. Here, guys, how about this? How about this? You guys ready for this? Okay, numerical example. What if resistor A is 1 ohm, resistor B is 9 ohms? You guys got that? Right? 1 ohm and 9 ohms. What if I have a 100-volt battery? Is it the same 100-volt drop across both of those? Yep, sure is. Same 100 volt. All right. Now the current splits different ways. That's different. But the voltage drop is the same. Same voltage. That's related to the loop rule. That's all right. Oh, Blake and Chloe running away with the lead. 2 lamps, thick filament, thin filament. So low resistance, high resistance, connected in parallel, just like before. The current is larger in the lamp with. Where's more current going? Yeah, thick filament. And the connecting fact is, guys, thick filament has what kind of resistance? High or low? Low resistance, right? That was yesterday's lab, right? Right? Thick filament, low resistance. And then, here let me switch over just to point out the exact rule that I'm looking at. I'm looking at this rule right here, right? And so more current in parallel, so the current splits, and more current goes through the path of least resistance, is what this is right here. Okay? All right, so that's that rule. All right, Casey, Tucker, Sophia, Blake, Chloe. Two lamps, thick filament, thin filament. So low resistance, high resistance. Connected in series, back to series, to a battery. The voltage is, I should say the voltage drop greater across the lamp. It's not the gold answer. It's either the red or the blue. Where is the voltage drop greater? Oh, no winners. No winners. Here. And so that's this row right here. And so the voltage is going to step down a little bit at a time. Guys, ready for a numerical example? Suppose I got a 9-volt battery. Oh, here's 9 volts right here. You guys see 9 volts right there? 9 volts. Everybody look up here. Look up here. Right. And I got 1 ohm versus 2 ohms. You guys got that? 1 ohm versus 2 ohms. How many volts drop across 1 ohm? Here. Guys, is everybody look up here? Everybody look up here. I got a 9-volt battery. Yeah, you're right. 3 volts. 3 volts. Because 1 ohm compared to 2 ohms, this is a third of the total resistance. Yeah. A third of 9 volts is 3 volts. How many volts drop across the 2 ohms? 6 volts. Exactly, because 2/3 of 9 is 6. Right? You guys got that? So it drops 3 and then drops 6. And then it gets pumped up 9. So up 9, down 3, down 6. Up 9, down 3, down 6. Okay? Got that? Okay. And then, okay, so the larger resistance, the more the voltage drop. And that's going to correspond to the thin filament. Okay? All right. You want someone else to do that? Not will. 70-watt bulb connected to a 12-volt car battery. Another 70-watt bulb is connected in parallel. What happens to the battery's output energy? Oh, I thought you guys were going to get that one. All right. Yeah, so yes, there's more energy. Here, let me find a parallel poster. Here's parallel right here. Guys, everybody look up here. Here. Right, so suppose you start with this. Right, so I got my voltage source like that cell phone battery the other day and one Christmas light. You guys see that? Or you start with that. And then you tag on another Christmas light in parallel. That one also lights up too, right? Because what is the brightness of this one compared to this one? They're the same? And what was the brightness compared to what it originally was? Isn't it just as bright as it was before? It's the same voltage over the same resistor, right? And then what if you throw in a third bulb in parallel? Now, is that one just as bright as the other ones are? Right? Right? So yeah, every time you add on another bulb in parallel, see the same voltage drop across a new resistor. So that's even more current that's being sent out by the battery. Tucker getting some points. Total resistance of 9 ohms and 10 ohms in series. Oh, I don't know. 19. 10 plus 9 is 19. So that's in series. Right? Who said it? All right, lots of points. Oh yeah, lots of points. The total resistance of 4 ohms and 4 ohms in parallel. Is 2 ohms. All right, nice. All right, so you can do product over sum. That'd be 16 over 8, which is 2. You can think about the painting a fence analogy. 4 hours and 4 hours. 2 man team is now 2 hours. Replace hours with ohms. All right, 4 and 4 in parallel is 2. All right, got Adam, Tucker, on fire with the scrum wrapper. Sophia, Blake, Chloe. Current through 2 identical light bulbs connected in series is 1 amp. The total voltage across both is 140 volts. What's the resistance of a single bulb? Here, I'll walk through this with you guys. All right, so we got 140 volts. I got my calculator here. 140 volts. Let's do Ohm's law. Can you guys say I equals V over R? Swap that around, make R equals V over I. So what is 140 volts divided by 1 amp? It's that 140 ohms total resistance. But it's 2 bulbs in series. So could that possibly be 70 ohms and 70 ohms in series? So each bulb is 70 ohms. You guys got that? About a series. Okay. Should be the gold answer. Okay, you guys saw that? All right, here. What if you do this whole thing backwards? If you have 70 ohms in series with another 70 ohms, it makes 140 ohms. If you connect 140 ohms resistance to 140 volts, that results in 1 amp that flows, right? Because Ohm's law, I equals V over R. Okay? Right, there you go. All right. Sophia, Blake, Chloe, getting some points. Ooh, true, false. In order to make a flashlight bulb light up, all you need to do is run a wire from the positive terminal of the battery to the bulb's base. True. False. All right. Half right, I suppose. Flashlight schematic. Right, so here's the schematic. Here's more close to what a flashlight is. Okay. All right. So voltage source. There's the battery. Right. Now, guys, if all you do is run the positive lead to the base of the bulb, then that's an open circuit. Is that going to light the bulb? No, that's not going to light the bulb. Right? You need the other half of the story. You go from the negative terminal, which is here, back to the negative lead of the battery, and also you need to make it a closed circuit. Right. So I have 3 things going on in this schematic. Voltage source, resistor, which could be a bulb, and I also threw a switch in there. Right? But if you want the bulb to light, it has to be a closed circuit. So if you hit the on switch, you can close the circuit and the bulb will turn on. Yeah. Right, yeah, you need a complete path for the current to flow. All right, got Adam, Tucker, Sophia, Blake, Chloe. When light bulbs are connected in series, they all carry the same current regardless of their resistances. True or false? First with the T. True. Oh yeah, true. That is here. Remind you guys where you saw that. That's this one right here. Hey, that's this right here. Here. It's the same current. Even if they're different resistors. Points. In a series circuit, the total voltage drop across a series of resistors is the sum of voltage drops across each individual resistor. True or false? True, right? That's related to something called Kirchhoff's loop rule. Here, let me show you guys a couple perspectives on that. Right? So that's like in any loop, the voltage is sum to zero. Guys, look up here. So remember before it'd be like up 9 volts, down 6, down 3. So up 9, down 9, right? This is also a reason I've been giving you guys these waterfall models and have you guys draw these waterfall models. Because you guys know like the deeper the dam, the more the pressure, the more energy you can get from a hydroelectric dam that way, right? So voltage, that's kind of like pressure. That's why I'm giving you guys these waterfalls, right? So you can pump, say, water up a cliff. That's like pumping electricity up using a battery. There's some voltage supplied by a battery, right? Boom, got battery. Bam. Right. Then each waterfall could represent a voltage drop, and the height of the waterfall is proportional to that voltage drop, right? Something like that. So suppose you have a so many volts battery, and then these 3 resistors in series will drop a little bit, little bit, little bit, and the sums of these waterfall heights matches the height of the cliff to begin with. Okay. Wahoo! Next question. Oh yeah. True or false? In a parallel circuit, current in each branch is the same. Yep, that's a false statement. I switch over here real fast, point out the rule. Okay. So we're talking about this rule right here. So in a parallel setup, the current splits, and the current through each branch is proportional to the other resistor, right? Because more current's going to flow where there's less resistance. Ooh, Blake taking top spot.
Yeah, Blake.
And a few questions left. Schematic diagram is a simplified, blocked out picture of a circuit in which the parts of the circuit are represented by symbols. True or false? True. Oh yeah. Lots of points. Got Adam, Tucker, Sophia, Chloe, Blake on fire. When resistors are arranged in parallel, their overall resistance is less than that of the smallest resistor. That is actually true. Okay, let's do a painting a fence analogy because that could be in parallel, right? Okay, suppose it takes you an hour to paint a fence, and your friend is kind of special. It takes him 99 hours. Okay, right? Now, if you team up with your special friend, is it still overall going to take you less than an hour? Yeah, maybe a little bit less. We could, right? Because you paint most of the fence. Maybe your friend over there is like, paints like a little line. But overall, it still takes a little less than an hour, right? Right? Now replace hours with ohms and friends with resistors. And there you go. So if you have 1 ohm and 99 ohms in parallel, overall it's going to be a little bit less than an ohm. You do product over sum. You confirm that, right? In order to prevent overloading in the circuit, fuses are inserted in the circuit. Yeah, true. All right, go fast. Let's look at the picture. All right, there's a fuse. Oh, guys, I think this very last question coming up is also related to that. All right, so you guys see how that fuse is inserted to make it work? If too much current flows, it's gonna break that fuse, and then the current stops flowing. But it only works if you have the fuse wired a certain way? And I think that's the next question. All right, so here's Adam, Tucker, Sophia, Chloe, Blake on fire for the win. A fuse or circuit breaker used in a circuit is usually inserted in parallel, true or false? Correct. False. Yeah, it has to be in series, right? If it was in parallel, it'd be pointless because the current would just flow a different path. Yeah, it has to be in series. Series is the answer. Right, to the podium. Who won Kahoot? With the bronze, Sophia. With the silver, Owen. And the gold, Blake. Runners up, Tucker and Adam. All right, nice job. Nice job. Oh, that takes us right to the end of class, right there. Nice job, guys.